Mr. Teachers and my fellow friends. So today our group are going to present our group assignment 1, which is the system of linear equation. So my name is Ong Hui Jin, and I will do the introduction of this group assignment. And here is our group members, which is Chun Zihan, our group leader, Yong Wan Ni, Lo Shiya, Ong Hui Jin, which is me, Tay Yuan, and Yong Vincent. And this is our matrix number. And this is for the SSCE 1693, Engineering Mathematics 1, Section 34. Okay, so you might be wondering, what is a linear equation? So linear equation, we can summarize it into this format: am1 x1 plus am2 x2 plus dot 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 plus amn xn equals to bm. So you might be have some question. What is a? Okay, so a is a coefficient, x is the unknown, which is the variables, and the b is the constant. Okay, it's not a linear equation. Not a linear equation is ax y. It has two unknown variables. Then that is not a linear equation. So if a linear equation has the solution has the real values if it satisfies every equation in the linear system. How can we say it? So I give this x plus 2y equals to 1. Okay, so this is our linear equation. Okay, sorry, negative 1. Okay, so this is our linear equation, right? And this is x1, this is x2. Okay, so I make it as a y, and my x must be 2, must be 1, and y must be negative 1 to make this to make the left hand side equals to right hand side. Yeah. So if the solution is not exist, the system is inconsistent. Okay, so we can summarize it into, so now if we have this 3-row linear equation, we can summarize it into a matrix form, which is like this: x equals to b, a is equals to coefficient, x is the unknown variables, and b is the constant. Okay, so we can solve the linear equation in 4 ways, which is the Gauss method, Gauss eliminating method, Gauss Jordan eliminating method, Cramer's rules, and the inverse matrix. Thank you.
I want to talk about Gauss elimination and Gauss-Jordan elimination. So both of these are methods to use for solving system of linear equation. So I have an example that I have got 3 equations. I have x minus 2y plus z equals 2, 2x minus 3y plus 4x equals 5, and negative x plus 3y plus 2z is 1. So the first step we are going to do is construct augmented matrix. We take the coefficient of all these numbers. Then step 2 is we use ERO to transform this matrix into the Excel matrix. And finally, we will got entries below the leading one become 0. So now is step 3 that we can solve it using back substitution. Look at row 3, we have 0x plus 0y plus 1z equals 2. So this simply means that z equals 2. And by substitution, we will finally get x is negative 6, y is negative 3, and z is 2. So now you look at Gauss-Jordan elimination, which bringing augmented matrix to a reduced echelon form. So first thing first, step 1 and 2 will be set. But the difference is that make sure just ones along the diagonals and zeros everywhere else using ERO. So we will get 1, 0, 0 equals negative 6, 0, 1, 0 equals negative 3, and 0, 0, 1 equals 2. So we can just read off the answer like we got last time. X equals negative 6, y equals negative 3, and z equals 2.
Inverse matrix method can be used to solve the system of linear equations too. If the determinant of A matrix is not equal to 0 and AX is equals to B, we can solve the system of linear equations X by multiplying A inverse with B. Now, let's see how we can get the equation as the previous slide. Ax equals to b is the given system. Next, we pre-multiply the both sides by A inverse. Based on the associative property, we can group A inverse and A together and the others remain the same. Then for the inverse property, when we multiply A inverse with A, we will get the identity matrix which is I. And for the last step, the identity property is that when we multiply I with x, we will get back x. And therefore, to find x, we can simply multiply A inverse with B. Let's see a simple example here. Consider the following system of linear equations and write them in matrix notation as the slide shows. The first step we will need to do is to check whether the determinant of A is equal to 0 or not. As the slide shown, the determinant of A is equal to 1, so there is an inverse for matrix A. The next step is to find the inverse of A. We can either use the adjoint method or the ERO method. By using adjoint method, we will first need to find the cofactor matrix. The formula and the steps are given here and we will get our cofactor matrix by combining all of our cofactor here. The next step is, after finding the cofactor matrix, we continue by finding the adjoint of matrix A. The formula is given here and this will be the answer. Then we can find our A inverse by applying the formula shown. And this will be our A inverse. We can also use ERO method to get A inverse. We will need to perform ERO until we get the new augmented matrix as shown. And this will be our answer for A inverse. For the last part to solve our system of linear equations, we need to apply the equation x equals to A inverse multiplied with b. After multiplying, we will get our answer as shown in the slide.
Cramer's rule is another method of solving system of linear equations. So given that the system of linear equation Ax equals to b, where A is the coefficient matrix and it must be a square matrix. That means the row and column of the coefficient matrix must be the same. X is the column matrix with the variables, and B is the column matrix with the constants, which are on the right side of the equations. So this is the general equation for Cramer's rule. So for the first variable, it will be the determinant of A1 divided by the determinant of A. And second variable, it will be the determinant of A2 divided by the determinant of A, and so on. So because of determinant of A is the denominator, so it must not be equals to 0, or else there will be no unit solution to the system. So for I equals to 1, 2 until n, where AI is the matrix found by replacing I column of the A with B. Consider the following system of linear equation. We can get the matrix A as the coefficient and matrix B as the constants on the right side. So with these two information, we can try to solve the system of linear equation. First, we need to find the determinant of original A matrix for the denominator. Since it is 1 and it is not equals to 0, we can continue to solve. If it is equals to 0, we may terminate the solving process as there will be no unit solution. Next, we get A1 by replacing the first column with B. So the value of 1, 2 and -1 will be replaced by 2, 5 and 1. This is our A1 matrix. Then we can calculate the determinant of A1 as -6. This process will be the same goes to A2 and A3. So for A2, we replace the second column with B and get the determinant as -3. And for A3, we replace the third column with B and get the determinant as 2. After that, we calculate the value of x by divide the determinant of A1 with determinant of A, gets -6. And for y, by using the determinant of A2, we get -3. And for z, by using the determinant of A3, we get 2.
So now we are going into types of solution for system of linear equation. When we are solving the system of linear equation, we could classify the solution into unique solution, many solution, and no solution. It is the best for us to use Gauss elimination method to solve the system of linear equation. By using ERO, we could reduce the augmented matrix into this row echelon form, which when k not equals to 0, r belongs to real number, it is a unique solution. K equals to 0, r not equals to 0, it is no solution. Both k and r not equals to 0, it has many solutions. And for unique solution, there are many methods we could use to solve the system of linear equation, provided that the determinant of A not equals to 0. If the determinant of A equals to 0, it may be either many solutions or no solution. Hence, we could only use Gauss elimination method or Gauss-Jordan elimination method. For unique solution, the rank of matrix A equals to rank of augmented matrix AB equals to number of variables. For many solutions, for sure the determinant of A equals to 0. The rank of matrix A equals to rank of augmented matrix AB smaller than the number of variables. Here are the examples of system of linear equation for unique solution, and given a linear equation, by using Gauss elimination method, we could get row echelon form reduced from the augmented matrix AB. And from the row echelon form, we can know that the rank of matrix A equals to rank of augmented matrix AB equals to number of variables equals to 3. And also from the row echelon form, we could form 3 simultaneous equations, and by solving 3 simultaneous equations, we could get the values for x, y, and z. Hence, we can conclude that the system of the linear equation is said to be consistent and has unique solution. Here are the examples of system of linear equation for many solutions, and also by using Gauss elimination method, we could get row echelon form reduced from the augmented matrix AB, and we can see that the last row of the row echelon form matrix is all equals to 0. Hence, we can see that the rank of matrix A equals to rank of augmented matrix AB equals to 2, which is smaller than the number of variables. And from the augmented matrix, by letting Z equals to T, T belongs to a real number, we can substitute Z equals to T into the augmented matrix equation. And hence, we can get the values for X and Y. And there are 2 solutions with 3 variables, hence there is an infinite number of solutions. The system of equation is said to be consistent and has many solutions.
The system of linear equation is said to have no solution. The rank of matrix A is less than the rank of augmented matrix AB, and the rank of the augmented matrix AB is equal to the number of variables of the system of linear equations. So let's consider the following system of linear equation with 3 variables, and we try to write the system of linear equation into an augmented matrix. Then we use Gaussian eliminations to reduce the augmented matrix into echelon matrix, which is this. Okay, by looking at the augmented matrix, so we can notice that the rank of A is equal to 2 because the first 2 rows of the matrix is non-zero, so the rank of it is 2, while the augmented matrix AB, all the 3 rows has non-zero term, and hence the rank is 3. So we can notice that the rank of matrix A is less than the rank of augmented matrix AB, and the rank of the augmented matrix AB is equal to the number of variables, which is 3. So we say that the system of linear equation has no solutions. So in conclusion, there is 4 methods that we learn in this subtopic to solve system of linear equation, which is Gauss elimination methods, Gauss-Jordan elimination methods, inverse metric methods, and Cramer's rule. So there's also 3 types of solution we can get, which is unique solution, many solution, and no solution. So as reference, we refer to the Ace Ahead STPN text Mathematics T first term, and also the Engineering Mathematics published by UTM. We also refer to some of the website and video online to help us to complete this assignment. So that's the end of our presentation. Thank you for listening.